Chapter 1, Real Numbers. The presentation is structured as follows. 1.1 Introduction. 1.2 The Fundamental Theorem of Arithmetic. 1.3 Revisiting Irrational Numbers. Introduction. This chapter will cover the following key concepts. Euclid's division algorithm. This principle describes how any positive integer a can be divided by another positive integer b to yield a remainder r that is smaller than b. The fundamental theorem of arithmetic. This theorem states that every composite number can be uniquely expressed as a product of prime numbers. Applications of the fundamental theorem. The theorem is used to prove the irrationality of numbers like the square root of 2, and to determine if the decimal expansion of a rational number is terminating or non-terminating repeating. The fundamental theorem of arithmetic theorem. 1.1 Fundamental theorem of arithmetic. Every composite number can be expressed as a product of primes, and this factorization is unique, apart from the order in which the prime factors occur. This means that a factorization like 2 times 3 times 5 times 7 is considered the same as 3 times 5 times 7 times 2. Generally, a composite number x is factorized into primes written in ascending order. For example, the prime factorization of 32,760 is 2 times 2 times 2 times 3 times 3 times 5 times 7 times 13, which can be written using powers as 2 cubed times 3 squared times 5 times 7 times 13. HCF and LCM by prime factorization. Example 1. Check if any value of 4 to the power of n, where n is a natural number, can end with the digit 0. Solution. For a number to end in 0, its prime factorization must contain the prime number 5. The prime factorization of 4 to the power of n is 2 squared to the power of n, which only contains the prime number 2 contains the prime 2. The uniqueness of the fundamental theorem guarantees that no other primes are in its factorization. Therefore, no value of 4 to the power of n can end with the digit 0. Example 2. Find the HCF and LCM of 6 and 20. Solution. The prime factorization of 6 is 2 to the power of 1 times 3 to the power of 1. The prime factorization of 20 is 2 squared times 5 to the power of 1. HCF, highest common factor, is the product of the smallest power of each common prime factor. Here, the HCF is 2 to the power of 1, which is 2. LCM, lowest common multiple, is the product of the greatest power of each prime factor involved. Here, the LCM is 2 squared times 3 to the power of 1 times 5 to the power of 1, which is 60. A key property for any two positive integers a and b is HCFA b times LCMA b equals a times b. More HCF and LCM examples. Example 3. Find the HCF of 96 and 404, and then find their LCM. Solution. The prime factorization of 96 is 2 to the power of 5 times 3. The prime factorization of 404 is 2 to the power of 4 times 3 times 13. The HCF of 96 and 404 is 2 to the power of 4 times 3, which is equal to 124. The LCM of 96 and 404 is 2 to the power of 4 times 3 times 13, which is equal to 3000, and 96 404 is 2 squared times 101. The highest common factor is 2 squared, which is 4. Using the property highest common factor times lowest common multiple equals product of numbers, the lowest common multiple is 96 times 404 divided by 44, which equals 9696. Example 4. Find the HCF and LCM of 6, 72, and 120th solution. 6 equals 2 times 3, 72 equals 2 cubed times 3 squared, 120 equals 2 cubed times 3, 3 times 5. The HCF is 2 to the power of 1 times 3 to the power of 1, which is 6. The LCM is 2 to the power of 3 times 3 to the power of 2 times 5 to the power of 1, which is 360. Remark. The product of three numbers is not equal to the product of their HCF and LCM. Revisiting irrational numbers. An irrational number is a number that cannot be written in the form p divided by q, where p and q are integers and q is not 0. Examples include the square root of 2, the square root of 3, and pi. Theorem 1.2. Let p be a prime number. If p divides a squared, then p also divides a, where a is a positive integer. Proof summary. If p divides a squared, then by the fundamental theorem of arithmetic, p must be one of the prime factors of a squared. The unique prime factors of a squared are the same as the prime factors of a. Therefore, p must also be a prime factor of a, which means p divides a. Proof that the square root of 2 is irrational theorem 1.3. The square root of 2 is irrational. This is proven using a method called proof by contradiction. Assume the opposite. Let's assume the square root of 2 is rational. This means it can be written as a fraction a by b, where a and b are integers with no common factors other than 1. They are coprime. Rearrange the equation. Squaring both sides gives 2 equals a squared by b squared, which rearranges to 2b squared equals a squared. This shows that a squared is divisible by 2. Apply theorem 1.2. Since a squared is divisible by 2, a must also be divisible by 2. So we can write a equals 2c for some integer c. Substitute and simplify. Substituting a equals 2c back into the equation gives 2b squared equals open parenthesis 2c close parenthesis squared, or 2b squared equals 4c squared, which simplifies to b squared equals 2c squared. Find the contradiction. This result means b squared is divisible by 2, and therefore b must also be divisible by 2. If both a and b are divisible by 2, they have a common factor of 2. This contradicts our initial assumption that a and b are coprime. Conclusion. Since our initial assumption led to a contradiction, it must be false. Therefore, the square root of 2 is irrational. More proofs of irrationality. The same proof by contradiction method can be used to prove that other numbers are irrational. Example 5. Prove that the square root of 3 is irrational. The proof follows the exact same steps as the proof for the square root of 2 by assuming it is rational, ab, and showing that this leads to a contradiction where both a and b must be divisible by 3. Example 6. Show that 5 minus the square root of 3 is irrational. Assume 5 minus the square root of 3 is rational, meaning it equals a over b. Rearranging the equation gives square root of 3 equals 5 minus a over b. The right side of the equation is a rational number, which implies that the square root of 3 is also rational. This contradicts the known fact that the square root of 3 is irrational, so our assumption was wrong. Example 7. Show that 3 times the square root of 2 is irrational. Assume 3 square root 2 is rational, meaning it equals a over b. Rearranging gives square root of 2 equals a divided by 3b. The right side is rational, which implies the square root of 2 is rational. This is a contradiction, so our assumption was wrong. Exercise. This slide contains exercise problems for practice, including proofs that the square root of 5 is irrational and that expressions like 3 plus 2 square root 5 and 1 over the square root of 2 are irrational. Summary. Here are the key points studied in this chapter. The fundamental theorem of arithmetic. Every composite number has a unique prime factorization. Prime divisibility property. If a prime number p divides a squared, then p also divides a. Proofs of irrationality. You have learned the method to prove that numbers like the square root of 2 and the square root of 3 are irrational. Thank you for learning with us.